Hi, good afternoon. So, welcome to this second session of deep learning for computer vision. So, I'm Abhip Shah. I'm a third year PhD student at Indian Institute of Science, and today we'll walk through. So, we are in the initial stages of this course. We are going through some of the pre-deep learning tools that we used to use some years ago and which are also very popular to this day. So we believe that alongside learning deep learning, you should get to know about these image processing tricks that were there in the pre-deep era. So let us get started. Okay, so yeah, like I said, this is the second live session, and so last day we had gone through some preliminary concepts of image processing. So this today we'll be talking about little more sophisticated things like edge detection and feature extraction. So we all know that nowadays with deep learning we do a lot of feature extraction. So there's a lot of models available out there which you'll get to know eventually, but how people did that in the pre 2012 era, so how those detectors were formed, that is one of the main agendas for this week. So sir has already gone through those algorithms in a great detail. So we will not go through all the details, but we will give you some examples on these different techniques, and then we'll so any algorithm, to understand it from the code, you should learn how to code it up. So going through the code of it gives you a little bit more detailed perception of the algorithm, of what is going on inside it. So we'll go through the algorithms of some of these and we'll go through the codes of some of these algorithms, and hopefully you'll find it useful. So edge detection, right? So first of all, what is edge detection? So you are given an image like this. You are given an image like this, suppose, and you want to so what you want is, you want an algorithm which will tell you what are the edges that are present in this particular image. So what is an edge? An edge is a sharp change in your in the pixel values. So for example, let's take this thing. So here it's dark, you can see on this side it's dark. So suddenly when you are going from this dark side towards this, you encounter these white pixels, right? So this line of white pixels that is there, that has come suddenly from the black pixels, that is what we call as edge, right? So edges are very useful in multiple applications. So one thing is understanding of the image by the machine. So if the image can point out what the edges are, then for a particular image, then obviously it has some understanding of that image, along with deeper understandings like along with deeper understandings of things like what are the objects that are present, how are they present in the image, and so on. So edge detection in our view is something that is very fundamental, very important, and it's something that, so some of the algorithms that we show here, so they are used even to this day in this era of deep learning and huge models. Even then these edge detection algorithms are still very popular. So how to do this, how to detect the edges, how to detect that these are the different edges of the different objects. So you can see that this is a very complex image consisting of a lot of lines, of a lot of change in the pixel values across the different edges. So how do we detect it? So one is the maxima or minima detection. So why maxima or minima? So I again answered this question before only, because you were suppose in this black area, when you were there, it was a pretty constant sort of area, low frequency, there was hardly any change, right? So you are moving upwards like this, and suddenly you encounter a huge amount of change, right? And then again once you cross that change, you again encounter some, you know, smooth non-noisy regions basically. So that is why people detect edges using minima or maxima wherever, so they find the gradients, and wherever there is a huge amount of change, we call that as an edge. So that is given by the minima or maxima. And in other words, it can also be given by the zero crossing in the second derivative. So if you take the suppose you take the first derivative here, and so you are going, so suppose you take the first derivative and then you take a derivative of that once again. So the minima or maxima will be where the second derivative is going to be 0, because that's a, you know, that has a slope of 0. So basically there are two ways to find the edges. One is the maxima or minima detection, and second is the zero crossings in the second derivative. So if you have not gone through this, I suggest you go back to Sir's lectures. So they will be in much more detail in those lectures. Okay, so some popular edge detection algorithms include the Sobel operator. There is the canny edge detector. So we will go through the canny edge detector in the code directly. So I am not going through it in the slides. But yeah, Sobel is an operator. So again, like we were talking last day about you know, window based functions. So this is again some sort of a filter that is given to you, which is helpful in detecting what edges are here. So now, so these operators can be divided into x component and y component. So this is the x component and the matrix for that. So if you have an image A, you multiply that A with this particular matrix. So sort of like a correlation operation, like we were discussing last week. So you do this with, for the x component, you do this for the, you multiply with this for the y component. Okay. So what does this signify basically? So if you multiply, suppose so this gx that you can see, okay, so let's do it in this way. So suppose this is one such you know, operator matrix that is there. So now when you superimpose this on the image itself, so you can see that everything is color coded. So these are all yellow in color. So the yellow parts will match with the yellow, these column, this particular column will match here, the 200s here. Then this part, this middle one, including this middle 0 will be here, and this this part will fall here, right? So this will have a high value when you have a sudden change, right? So suppose here, when you are here in 200, then you are here from, so you were at 100, 100, 100, 100, 100, 100. So this is what, this was very like constant in nature, right? So yeah, sorry. So this was constant, this was constant. Suddenly from being constant, you move to something quite different. So this is an indicator of the fact that an edge might be present in this location, right? So that is modeled by, those kind of changes are modeled by this particular matrix. So your central pixel, which is here, it's trying to see like what is in the left neighborhood. So these three, what is in the right neighborhood. So these three, so are they very different or not? So that is what this particular matrix is trying to measure, right? So if the values are very different, then that means that there's an edge here. This particular pixel probably is part of an edge. So that is all that is there to these kind of operators, right? So this is the x component, like I said, this matrix, and this is the y component. So now what we do is, for we pass, so these two matrices that are there, these two filters that are there, we pass them through the entire image, right? Just like we do convolution or correlation, whatever. So we pass this image. So the first time it will be like this. So you'll place it in the first 3x3 patch. Then we'll move one step right, and then we'll place it on the second 3x3 patch, and so on. This will continue doing till the end. And now at the end, what we will get is, we will get 4 values, because the central pixels are this, this, this and this. So we will get 4 values. So 4 values means one value each for gx and gy. So in total we will get 8 values. So here we will get one gx value, one gy value, again one gx value, one gy value, and so on for these 4. So now what we will do is, at every pixel location we will take this gx value and we will compute this basically. So we will do gx square plus gy square and take a root over of that. So that value, this value gives us the magnitude of the edge, right. So this is given by this g, and we also can find the orientation of the edge. So that is given by, so this is basically tan inverse. So generally however we find the angles, we do a y by x generally. So y component by x component. So similarly this is a tan inverse of gy by gx. So that gives us, like, if there is an edge at a particular pixel location, what is the likely location, what is the likely orientation of it. So that is, this entire thing is given by this operation. And suppose now if your value is, suppose, so you are calculating this g value over here over this pixel location. So now if this value is too low, right, so then we do not consider it to be an edge. But suppose if this value, the resulting value that we get of this g, if it's below, if it's above some threshold, then we consider it to be an edge. So similar to Sobel operators, there are multiple other operators like Prewitt, Robert. So all of them are very similar in structure. So just remember that this gx is meant for detecting vertical edges, and this gy is meant for detecting horizontal edges. Why horizontal? Again, because if you, instead of this particular filter, if you take this filter, you will see that at a central location, what I am trying to do is, I am trying to see what is there on the above me here and what is there below me, and are these two very different from each other. If they are very different, then that means that I am likely an edge point, right. So this is how, because this is above and below, that means I am trying to detect an edge which is likely horizontal in nature. Similarly this one, since the zeros are across the columns, this is likely vertical in nature. So keep in mind this, these few short things, small things. So I don't know if this is very visible or not. So I would suggest you to go back once we upload the slides. You can go back and have a look at it, exactly like what is going on here. So but what we want to do is, given this particular image, we are trying to find the edges using the Sobel operator that we saw, right. So one thing, so this particular left side value is one, when you find the edge using the what do you call it, using the y operator, y filter, gy, and this is what happens when you use it with the detect the edges with the x operator, x filter basically. So here once you go back, I don't know if it's very visible or not at this point, but once you go back, you will see that for this one, because this is y, it's detecting the horizontal edges much better. So you can see this one, if it's a little bit visible to you, this one, these edges, it has detected very well, whereas this entire part where the leg of the table was, this is completely blank, okay. So that this is because the y part is looking for horizontal edges, hence it is able to detect these things, this table's edge here, this thing here. So these things it is able to identify, but not these things. Similarly in the x part, you will see that the table, if it is visible to you, you will see that the table's leg is now much more visible, the chair's legs are visible actually. So your but however the horizontal edges this time are not really visible here. So this part is not there in this image. So this shows that the y part, the gy that is there, the one that is given here, this is much better for horizontal edge detections, and this x part is better for the vertical edge detection. But when you combine these two to get the magnitude and the angle, you can detect edges of any type. So that is why we are showing this. So this image, so this image is an example of what happens when you use the Sobel operator, and so these are the edges detected by the Sobel operator, and you can see that when you combine the gx and gy, you are able to detect the edges pretty well. in this image, right. So yeah, so like I said, so if you take this image once again and instead of using just gx and gy, you combine them, you now see that if it's visible to you, you can see that you can detect these edges pretty well now. So the vertical edges are visible, the horizontal edges are visible, so more or less it's a pretty good performance for detecting the edges. So this is the Sobel operator, and like I said, the Prewitt, Robert operators, all of these are very similar looking operators with that one agenda that I have to see whether at my location whether there is a huge difference between my left neighborhood and right neighborhood or not, and similarly whether there is a huge difference between my upper neighborhood and lower neighborhood or not. So that is what these operators are trying to do. So out of all these operators, the canny edge detector is probably the most popular one. So right after we complete the slides, we will go through the canny operator and we will go through the code of it. Right. Now we will also revise SIFT a little bit. We will also revise SIFT a little bit. So what is SIFT? SIFT's full form is scale invariant feature transform. So sir has already gone through it in a lot of detail, but still we would like to give some overview of what SIFT is doing, and after that we will also look a little bit at the code of it. So SIFT is something, so why do we need features at all? So basically suppose you are given two different images containing similar objects, right. Now it's always not possible for the humans to manually identify whether given two images have any similar objects or not, what is going on, whether one image is a rotated version of another or not. So we always needed computer help. That is why we built computers, right, because we wanted to create algorithms which will automatically do this for us. So we do not need humans anymore to do this. So in the deep learning era, which you will get to know in a next few weeks, so this feature detection, it itself is a very big topic in the world of deep learning, and nowadays through the deep learning models we are able to detect very good features out of a image. Features means kind of like what is the main semantic content of the image. So that is what we represent as features. So so deep learning, again if we look at the difference between deep learning and this sort of algorithms that we are going through now. So deep learning models, they are very data hungry models. So you need to collect a lot of images and you need to train your model using those images, and then your model is going to work well. So the more the images, the better your model is going to be. But these pre-deep learning models, while probably in recent times deep learning has crossed them, even then the speciality about these models, these pre-deep era models, is that these models are capable of working, they are not trained on any data. So they are pure simple algorithms, and when you apply them on any image, it will be able to give you pretty good results. So that's the good thing about these methods like SIFT and all. They are very fast, they are very efficient, and for at least in terms of nowadays, for simple tasks they are still good enough, right. So SIFT itself is not a very easy algorithm. So I would say that some of the deep learning algorithms are easier to grasp than SIFT itself. So there are 4 broad points which are used for for performing SIFT. So first is scale space extrema detection. So basically what you are trying to do is, given an image, you are trying to point out what are the interesting points, key points as we call it, to the image, inside the image, which are invariant to its scale and orientation, right. So we will look at what scale means and orientation also. So suppose if I give you what is an interest point to me. So if I give you a dog image where the dog is looking towards the left, right? And I give you a second dog image where the dog is looking towards the right. So just because these two dogs are looking at two different regions in the image, in the pixel space these two images are completely different. So suppose if you compute the L2, I mean the squared error difference between these two images, you will see that the value is actually very high. But ultimately these two images are looking at the same thing. It's a dog, one looking towards the left, one looking towards the right, right? So you have to identify that what is the dog in the image, right? So this interest point, which is the dog, should be same for both the images. They should be similar for both the images because they are referring to the same thing, right? So this first step is looking at interesting, it's trying to capture what are the interesting points in the image which are invariant to any scale or orientation. So it can be left oriented, right oriented, we don't care, using DOG, which is DOG is nothing but difference of Gaussians, right? So yeah, so that is the first point. Second point is that key point localization. So this consists of mainly two things, you can say. One is that when you detect interesting points in the step 1, so you may have detected many points that are actually they are very interesting, but probably they are not exactly in the correct location. Maybe there is a little bit of error in the locations that you found for these points. So key point localization, as the name suggests, it determines the correct location to the as much as possible. And also so again, step 1, the detected interesting points may be very, the number of such interesting points may be very high, right? So based on the algorithm that is applied here, which we'll see in a bit, but yeah, some interesting points may not be really as interesting. So this particular key point localization point, the algorithm that is applied here is used to eliminate some of these bad key points, basically, that are not important for us. So that is the second step. Third step is orientation estimation, right? So whatever key points are left with you after the second step, you are trying to find out the orientation of those key points, all of those orientations, using complicated algorithm which sir has already gone through, but just remember the names. So from the names you will get to understand what each of them means. So orientation, you are trying to estimate the orientation of all the localized key points, and finally using this orientation estimation and a lot of related stuff, you are finally able to assign some description to each of those interesting points. So basically the idea behind this entire algorithm is that you want to detect what are the interesting points in the image and you want to describe those points. So description we cannot do, at least in those days we could not do using text, right? So we would do that using some numbers in the form of vectors. So each interesting point would have some collection of, would have some vector associated with it to identify that interesting point, and that is what we call as the key point. So key point descriptor. So it's basically you are trying to generate the description for all the key points that you are trying to that you obtained in the previous steps, and you are getting a description for each of them, and using those descriptions you can even arrive at one single description for your entire image. So the output of this algorithm is one description for your entire image and also descriptions for the individual key points. So obviously, so in this particular talk we will not go through all the steps. It's just a reminder sort of that this algorithm is there and you should all know about it. So we will just touch upon the first two steps, scale space extrema detection and the key point localization. So these two they are much more coding oriented, they are much more algorithm oriented. So I request you to have a look at them on your own time, because sir has taught them in a lot of detail. So the first step is scale space extrema detection. So first step is like so we have this 2D Gaussian. So take an image to be a 2D matrix at this point. So, we have a 2D Gaussian whose formula is like this, and so it at a certain location x and y, and it has a it's defined for a certain location x and y, and it has a standard deviation sigma. So, now what you do is you compute this quantity called scale space, which is basically your this Gaussian convolved with your image at the location x comma y, right. So, that is what is known as the scale space. Now, next what you do is you compute something called DOG, which is the difference of Gaussians. So, difference of Gaussians is what? It's basically you are taking a difference of two Gaussians, one with standard deviation k, the other with standard deviation sigma. The first one is k sigma and the second one is sigma. So, you basically take a difference of them, convolve with your image, and the resulting thing is known as DOG, difference of Gaussian. So, basically why we are doing this is because DOGs are approximate, they are an approximate of the Laplacian. So, we know how Laplacians are very, so Laplacians have multiple functions, right. So, they can detect edges, they can detect blobs. So, all of this we have gone through in the week, but Laplacians, they are not easy to compute. So, they take up a lot of compute power. So, as scientists are, as engineers rather, our job is to make our lives as easier as possible. So, while LOG or this Laplacian of Gaussian is not an easy thing to compute, DOG is a much simpler thing to compute. So, it is nothing but the difference of these two Gaussians. You find the difference and you can convolve with your image and you are done, right. So, now once you compute the DOG, what you do is something like this. So, the DOG images, so DOG is again you take the difference of Gaussians and you have convolved with the image. So, they are grouped by octaves. Octaves are nothing but this is a bigger dimension. First octave is the bigger dimension image, in the second octave you have reduced the dimension of the image, and now based on these you so these are all Gaussians at different sigma values. So, this is suppose sigma 0, this is k sigma 0, k square, k cube and so on. So, now you compute the difference of Gaussians with respect to each of these pairs, right. So, one thing that to look at is what happens to this scale. So, suppose if I have this k and I so if what happens if I convolve a Gaussian kernel with an image with different scale values. So, if this is your original image, so when I convolve a Gaussian filter with a scale value of 0, that means there is no standard deviation at all, hence your image remains the same, right. The moment you have a scale value 1 means it is 1 into sigma, that is some sigma. You can see that the image has become much more smooth and it has also become blurrier because Gaussian is a smoothing filter, right. Similarly, now you have a scale 4, you can see that the images are becoming more and more blurry. So, this is this again in the scale 16 it has become a little bit more blurry, more blurry, more blurry. So, at scale 256 you almost are unable to identify what the image is, it is so blurry. So, this is what the so basically what we are trying to do in this particular example is with these different scales that we generated, we are trying to compute the difference of Gaussians and we try to find the interesting points in this space. So, the idea is that in different versions of these, in between different versions of these, we are trying to find out what are the important points that are there in this in between these two images. So, at different scales I am trying to see what interesting points are there in the image, right. So, octave is given like this. So, this is the bigger version, first octave, second octave, third octave, you can see the pattern. So, it is growing smaller and smaller. So, I do not know if it is visible or not, but this is the actual one. The more you keep on adding some Gaussian noise, it is becoming a little bit more blurry. So it's not very apparent here, but it's much more apparent in the smaller ones. So this was the original one in the second octave, a little bit blurry. This one is a little bit blurrier and blurriest. So like this. So this is what you want to do. Now in order to, so this is all very good. So here we have just, till now we have only detected the difference of Gaussians, right. So we have these difference of Gaussians. So now how do we finally detect the interest point? So remember, the primary objective of this step was to detect the interesting points, the interesting key points that are there invariant to scale, right. So we have already taken care of the scale here, we have taken the difference of Gaussians. Now we are left with the activity of detecting the actual interesting points. So what we do here is, so we extract a local extrema in the DOG pyramid. So the DOG values, the DOG pyramid that we saw here in this slide. So we what do we do here? We are trying to extract the local extrema in this pyramid. In what way? Suppose this is one of them, this is the below one, this is the upper one. So now we take, suppose we have a patch here, right. We take a patch here, a window here, right, and we take the central pixel. So whenever we are operating in windows, our most interesting point is the central pixel. So now what we will do is, this particular pixel we will compare against all the points here all the points here, all the similarly located points above and all the similarly located points below, right. So this means these are 9 points here in this particular window. In the same location here there are 8 points, because this is the interest point itself. This is the point itself that I am trying to see whether there is an interesting point here at all. So this cross one. So I look at the neighborhood of it. So these are 8 points because I have excluded this, and here below these are again 9 points. So 9 plus 9 plus 8 equal to 26, right. So compare each point to its 26 neighbors. Okay, 8 at the same level, 9 above, 9 below, right. So now if this point is interesting, it's either smaller than all of these or it's larger than all of its neighbors, all of these, right. So if it's something like that has happened, that if this cross point is actually higher than all these values or lower than all these values, then this point is somehow interesting to me because this is different, right. So this point is then, this cross point is then taken as a key point, as an interesting key point, and we mark it, right. So that is what we do throughout the entire image, right. So we mark all these interest points, and this is what the key points are. So given this image, when you run this first step, these are the key points that you get, right. So if you look at, so if it's visible to you, so all these key points are, you can see that there are many arrows over here. So the arrows mean what? That wherever these arrows are starting, that is your interest point, right, and the length of the arrow gives you how much the magnitude of that interest point. So how interesting is it? That is given by the length of the arrow, and the direction is given is representing the orientation. So on which side is my interesting point, I mean how is it oriented, right. So this is at the end of the first step, this is what you get into. Now what you will do in key point localization is basically you will try to see if you are, so here you can see that there are so many interest points that as a human you cannot even perceive what is going on. So it has detected almost everything as interest points. So some of them are very close to each other, like you can see here this part is very congested. All these parts are very congested, these window parts and all. So maybe some interest points are very actually interesting to look at, some are maybe not that interesting, they are not that helpful, right. And also maybe they are not, I mean their localization is not proper. So I have placed the interest point somewhere close, but it's still not 100% correctly spaced. So what I will do is, once I have detected the key points using the scale space extrema detection step, the first step, I will just hold on, yeah, right. So what I will do is, I will first run an algorithm to make sure that wherever I have placed the key points, I place them correctly. So maybe they are a little bit wrong, so I'll place them correctly first, and then I'll eliminate some of the key points because they do not look as important, right? So similarly to this, we have the third and fourth steps also, which I am not going into now, the orientation estimation and the key point descriptor, final key point descriptor, how you are getting that. So the orientation estimation is basically trying to estimate the correct orientation of your each key point based on your neighborhood. So and your key point descriptor is nothing but based on your, again based on your neighborhood, you collect what are the different orientations that are there of the different key points that are there in that particular neighborhood, and you are trying to form a description of that. So that is given by this key point description. So at the end of this algorithm, till now, I mean, whatever images we have shown, I hope we have been able to give you some idea of the first step, which is the most difficult one to grasp. The others are still, you know, some sort of algorithms. So I hope with these examples your ideas of the key point extraction, I mean scale space extrema detection, they become a little bit clearer. So yeah, and yeah, steps 3 and 4, as I said, so sir has taught it in great detail, so it's better that you look at those slides to understand it. So at this point, yeah, I would ask the others, like, if there is any doubt you can tell me, otherwise we can probably.
Can you please go to the previous slide?
Sure. This one?
No, it's previous.
This
No,
one?
my question is like once. No, no, next slide. Next one.
This one?
Next. Next. Yeah, here.
Okay, okay.
So here we have 26 neighbors for a
Hmm.
single pixel, right?
Yeah.
So is this? I mean, 3 by 3 is moving one stride every time, or
Yeah, it's something like that only. So you'll
because of
take each,
windowing?
you'll take each of these, suppose your, this one is your, this one is the image of your interest, right? So you'll keep on moving. So you'll basically try to see each of these pixels if there is an interest point here. So to do that, suppose, so this is just an example that whether the cross marked pixel is at all an interest point or not. In the next step, you will see whether this one, the next one, is an interest point or not. So you will just have a stride and you will move across the entire image. So in this way, you are basically trying to see in the entire image. So if you look at this one, what this has done is it has gone through all the pixels in the image, and it has tried to see whether at a particular xy location in the image there is an interest point or not.
So the thing is, each image has different scales, right? Like
Yeah,
now,
yeah,
in the because of this Gaussian scales.
yeah.
So every pixel in each image will be encountered, or like how?
Yeah. So what you will do first is you will compute this this what do you call it? Yeah, this scale space. So these are all different Gaussians, right? Gaussians with different standard deviations, where there's a sigma that is there for each standard deviation, but you multiply it with a k each time. So now you have made, so you understand what is meant by this scale thing. It's becoming, you are adding more and more noise to it basically. So now what you do is, so this is a single image. So now you compute the difference of the Gaussians here using these two, and you generate each of these, right? So now what you will do is, first you will take this one, and then you will see, like, for each of the pixels here what are the interest points, for each of the pixels here what are the interest points, and so on. So now at the end of this, once you run this algorithm entirely, you will see, like, combining all of these, what are all the interest points that you could gather. So that will give you this particular image. Just a second.
Okay, and there also we have different octaves, right? So
Yeah.
again, the same interest level interest point calculation is going to happen there
Yes.
also.
So it's like you are trying to, so one thing is, if you suppose if you have a big image, so there will be lot of detail in that image. So based on that, I mean, the more you so if you have a bigger dimension image, you are looking at the smaller details of the image. Now if you have made the image a little bit smaller, you are, suppose you have a face in the image, so that face is taking up maybe this particular portion in this particular image. Now here it will take up a much bigger I mean, if you take an equivalent size, if equivalent patch here, so what I am trying to say is that a 3 cross 3 patch in this particular image is not equivalent to a 3 cross 3 patch in this particular one. So here you will get a very small thing, here you will get a much bigger thing. So you are trying to look at the interesting points in the image at different scales. So at the bigger image also you are trying to see what are the interest points, and at the in the smaller scales also you are trying to see what are the interest points. So yeah, if it's not that clear, you can go back and look at the slides. The way sir has taught, that is much better. But yeah, the idea is something like this. So if I go back to this face, suppose I take a 3 cross 3 patch here, so that looks at only the eye, suppose. But now in this particular image, if I take a 3 cross 3 patch, that probably takes the entire face, or maybe here. So if I take a 3 cross 3 patch equivalently size 3 cross 3 patch, it will be like the entire face. So basically what you are trying to do is, in a bigger image, if you take a patch, it will look at a very small thing, and as you go towards the higher octaves, your image becomes smaller, but what you look at is a much bigger thing. So maybe here you look at one eye, here you look at the entire face. So you are trying to identify interest points at different levels of the image, so that you do not miss anything. So here, while this eye thing is very interesting to us, the face is also very interesting. So that's why I am trying to capture all of that. So that is why this octave thing is there.
Okay. And in this slide, so we are trying to find the difference. I mean, these 26 pixels are from the difference of Gaussian, right?
Correct. Yes.
So these three planes are like three different DOGs, right?
Yes.
Difference of Gaussians. Okay.
And why is that? Because DOGs are equivalent to LOGs. LOGs are Laplacians, and if you go back and see, Laplacians are good for detecting edges, good for detecting blobs. So Laplacians are basically very informative operators which give you a lot of information about the image. So to approximate the Laplacians, which are not very easy to code and not very efficient, you are performing these DOG steps. So all of these are in the DOG step. Yes. So like it's written here that it's done in the DOG pyramid. Pyramid means this one that I am getting. So you do that in this pyramid, and then you compute the neighborhood. If you are different from your neighborhood, in the sense that if you are lower than all of them or higher than all of them, then you are carrying something different. So you as a pixel, this particular crossed one, it's carrying something different from all the others, something very distinct. That's why we mark it as an interest point. Otherwise not.
Okay, thank you. So so all the key points at different octaves are also plotted in the
Yeah. They are finally mapped into the image.
Okay, thank you.
Yeah. Anyone else? Okay, cool. So let us then start looking at maybe we'll have a small look at the code here. So okay, let's do one thing. Let's open in Colab. So nothing to worry, all of you will get all these codes. So yeah, while it's loading, better that you go through these codes, you play with them. So this I keep on repeating to every batch. So the more, so like one of our friends was asking questions on SIFT. So some of these notations that I just give me a second. Let me present. Yeah. So some of these steps that are actually given here, they are pretty confusing in some cases. So not all of, so these diagrams you will see everywhere, but not the descriptions of them. So the best way to understand what is going on inside them is to look at the codes, play with them, I mean change them, write your own code, maybe insert your own image, etc., and see what is going on. So that is the best way that you can learn what is going on in each of these algorithms. So this is a particular code that I wanted to walk through with you, because this tells us about the Sobel filters that we just saw, and also in a while we will look at the canny edge detector also. So like I said, the Sobel filter is a edge detector, and it basically tries to perform a 2D. So let me do this. Yeah, I hope the font is better now. Yeah. So basically the filter measures the gradients, and it sees whether your gradient is reaching a maxima or a minima at some point. So that is given by the operator, the filter that I showed. So in this particular notebook, I'll rather give you a little bit too detailed description maybe, and then in the next notebook it will be a little bit faster. So here first of all we are importing all these libraries that are there. So those of you who are not well versed in Python till now, please go ahead and learn it. It's very simple, it's very handy, and the coding style of Python is just very similar to English. So it's not a pain to learn at all. So I request all of you to go back and learn Python as soon as possible. So these are some of the important libraries that we import for this particular activity, for this particular exercise, and particularly CV2 is one such. Its full form is OpenCV. So OpenCV is one such library that is available across languages, which is good for dealing with images. So we will this time. So last time we had looked at sklearn, and this time we are looking at OpenCV or CV2 in Python to operate images. So right, so the first step is so this is not a very important step, but what it does is it loads an image from which is stored somewhere on the net, and it will just read it. Okay, that's the first step. So now in this particular input image variable, I have put the image that I have read, and now I am storing the shape of that image. So this image is an RGB like it said here. So we'll also below we'll look at what the image is exactly. So RGB means what? So there are 3 dimensions in the matrix: x, some nx, some ny, and nz. So all of these we store in separate variables, right? And now what we'll do is we want to convert this particular RGB image into a grayscale one. So you do not have to be very, you do not have to look into this too much, because there are already libraries in Python that will do it for you. So nobody is going to ask you what is happening here. So basically just treat it as some transformation function. So I have all the 3 channels, red, green and blue. So in these 3 variables I'll load each of those. So R image means the red channel, green channel, blue channel, and I'm loading them in this way. So the 0h channel of the image, 1h channel and 2h channel, second channel. Now the next steps, they look a little bit difficult, but they are doing nothing but a grayscale conversion, and we need not go into this. So OpenCV itself has many functions that, it has its own function which will convert your it has its own set of functions which will convert your RGB image to a grayscale. So please don't be worried with this part, and I am not going to go into this. So this is the image that we had opened. So it's something like galaxy or something like that in the outer space, some image in the outer space. So now once you do this grayscale operation on this is what you get. It's a simple grayscale image which consists of only one channel, right? So now let's reduce this again. So now we'll look at the main part, which is the application of the Sobel filter. So like we told in the slides, Gx is a vertical kernel, Gy is the horizontal one. So again let's put the slides in the correct position so that we can refer. This was our Gx, this was our filter for the x component, this was our filter for the y component, right? So so it's already given here, sorry. So now what we'll do is we'll simply we'll put this Gx into an array. We'll define Gx to be this particular matrix, we'll define Gy to be this particular matrix. Done. So now what we will do is, again for the grayscale image that we had, we are storing the rows and columns, number of rows and columns of it. So treat the image as a matrix at this point. And now what you do is, in the next part, so all the comments are also given here if you notice. So you are initializing the output image to zeros, right? You have an input image, this one, you have an input image, this one. So we are operating on the grayscale here, and you are creating the output images variable, basically you are initializing it with zeros, and now you are performing the convolution operation. So what basically you are doing, so at the image, at every 3 cross 3 patch, you are multiplying that 3 cross 3 patch with individually gx and gy. Okay, so that is what we know as the convolution operation. So you can see here, you can go through it on your own time. So we are multiplying gx with the image at the particular locations, this particular location, and similarly we are doing the same thing for gy. We are convolving gy with that particular location. And now, like we said, again going back here, so what was our magnitude? Magnitude was gx square plus gy square and root over of that. So that is exactly what we are doing. So at the I plus 1 j plus 1th location, we are doing a gx square plus gy square, and this np dot square root basically computes your square root of a quantity. So it's a square root function, right? So if you so once you applied, so you can see one thing, that implementing this particular code is nothing. So all you have done is just implement whatever was given here. You calculated the magnitude and that's it, you are done. So this was the result. So this was the input image and this is the output. So you can see that if it's visible to you, so there is something over here, it's not very detailed. So this one you can see on the other hand has a lot of detail here. So all these brown things, they are not detected here, right? So yeah, so only this part, this particular edge probably has been detected, none of the other things. So this particular star has been detected, it's a little blob, and so on. Some of the stars have been detected, but it's not very well detailed. So Sobel, while it's a very useful tool, it's very easy to implement, very efficient. It's there are better algorithms out there. So these are some of the, we have attached some blogs and other resources for you to go through. But now let's look into the canny edge detector. So canny edge detector is by far the most most popular edge detector algorithm. So it's something that is used even to this date. So yeah, you should know it, and it's a very beautiful algorithm. So the algorithm, again like our SIFT, it has 4 parts. Okay, so these are the 4 parts. So yeah, so these steps you have to follow in order to perform canny edge detection. So first is you denoise the image, you filter. So how do you do it? You filter the image with Gaussian, okay, with a Gaussian kernel. So this derivative part is wrongly present, but yeah, you filter the image with a Gaussian. So you blur it, you smoothen the image basically, and now you find the magnitude and orientation of the gradients present in the image. So that will give you a hint of the edges that may be present in the image. So find all the magnitudes and orientations of all the gradients that you find. Next is non-maximum suppression. So non-maximum suppression, what it does is, very often in a single neighborhood you are you have found a lot of edge points, right? So that is actually bad. So if you have, suppose for example, so suppose, let's look at the table image only. So suppose I am trying to detect the edges here. So all I want to do is mark this, right? But instead of, so this I can, as a human, I can do with a single stroke. But suppose if my algorithm gives me lot of lines here, right, many lines here, so then that is bad. So non-maximum suppression is a small algorithm which will help you eliminate many of the unimportant edge points detected, right. So many of the unimportant edge points that are located to the in the neighborhood of the correct edge point. So they were also detected as edge points, but you already have a better edge point present in their neighborhood, so you would rather choose that edge point, right. So that is again, go back to the lecture notes, lecture videos if you want more information on this. And finally you have linking and thresholding. So like I said, in the Sobel operator, how do you know whether, so you will get G value for every pixel location, but how do you know that which G value is a edge point and which is not an edge point. So you have a threshold for that. So if your particular value is greater than a threshold, then you call it to be an edge point, otherwise not. Here in the canny edge detector, they are giving us multiple thresholds, 2 thresholds here actually. So one low and one high. So the algorithm says that if your threshold, if your value is greater than high, it's an edge point. If it's lower than low, it's not an edge point. And if it is between low and high, then I will not eliminate it. I will see if this particular point, this particular pixel value is connected to another pixel value which is an edge point. If yes, then I will consider this pixel value to be an edge point, otherwise I will eliminate it, right. So use the high threshold to start edge curves and the low threshold to continue them. Fine. So now given this particular algorithm, we will try to look at the code for it. So first again we will import some of the libraries. So here the new library is SciPy. So SciPy is again another Python library that is used, that is very important and very relevant for so that is very relevant and very handy for performing many mathematical operations. So I mean, make use of this, go through this and learn this. So this is just as important as the other ones. So first step that we said here was to filter the image with the Gaussian, with a Gaussian kernel. So that is what you are constructing here in this part. So you are constructing a Gaussian kernel. Next you read an image, and you convert it into grayscale. So like I said that grayscale you can do it in many ways. One was the one that we showed in the code, that was a very complex one, and this is in one line using the OpenCV library. You can do it in one line. So you have converted your image to a grayscale, and now this image is of 2 dimensions, where you can see that the values are between 0 and 1, they are normalized. And this is the image that we saw way up. So that universe sort of image, the image of the some part of the universe maybe. And now what I am doing is following the first point of canny edge detection algorithm, I am convolving the image with the Gaussian kernel with a standard deviation of this 5. So let us look at the function of Gaussian kernel. So this is sigma here is the initialization given here is 1, the default value is 1, but I am giving a value of 5. So now once I look at the, so you can see the difference between these 2 images. So this is a much more, so this was the original one, and this is a much more smoothed out version of the original one. You can see that it has become blurrier because of the smoothing, right. Now step 2, find the edge intensity and direction by calculating the gradient of the image using edge detection operators, right. So now what we will do is again the Sobel operator. So basically in this code book, in this notebook, what we are trying to give you is, on one hand we are trying to give you how to code things up, right. We coded up Sobel for you in the first part. In the second part we are simply like giving you some ideas on how you can do it very quickly, right. Some of the handy algorithms that are already implemented in Python. So you initialize the Sobel filters in the way that we had mentioned in the previous in the slides also. And also, so instead of the convolution operation that you wrote here, the big one, this ij loop that is there, you can also directly use a library function that is given here, right. So that gives you the edges, right, and this gives you the so these are denoted by ix and iy. So do not do not worry about these notations. So next what you do is you find the magnitude. How do you find the magnitude? Again going back, this is the square of the x component and the y component summed and then square root. So that is given by this function, right. So you take the ix and iy, and basically it is nothing but root over of ix squared plus iy square, right. And now you are normalizing and putting the scale from 1 to 255, and now you are trying to find the theta. Theta means the angle of the detected edges. So that is given by, so this arctan2 function is nothing but tan inverse of this iy and ix. So now you return g comma theta. So that kind of gives you like what are the edge points. So what is the magnitude of each pixel value, assuming that each of them were edge points, and what are the orientations, right. So now you call this function and you get the gradient matrix and the theta matrix using this Sobel filters. So this is, like I said, exactly the same code that we had in the some blocks above, just that we are using a convolve function that is provided by the SciPy library. Fine. So now again, once we look at the Sobel filter, you can if we visualize the resultant image, we can see that this is how it looks like. These are the edge points that are detected, and this particular image gives a feel of the orientation, right. So you can see that this is the gradient mat and this is the theta mat. So when we perform this on the theta mat, this gives a the orientation of the edges in the image. Now coming to non-maximum suppression. So non-maximum suppression is what it is trying to do is, so suppose you have, so I am not going to go through the entire code, but the gist of it is something like this, that okay, let me see if I can find it. No, let's not do that, let's go here. So basically in a nutshell, what we are trying to find out is that first of all I will try to see what is the, if I am a pixel, what is the magnitude of what is the edge magnitude that I gradient magnitude that I got. That is the first thing, and then I look at the orientation. So what is the orientation that I have as a pixel? So based on that orientation, so suppose that orientation is some maybe say 89%, okay. So if I am sorry 89 degree, so if I have an 89 degree orientation, so now what these guys have done, the creators of Canny, they have divided the 360 degree rather the 180 degree space into multiple buckets. So 0 to like they have given here 0 to 22.5, 22.5 to 67.5, 67.5 to 112.5 and so on. So all these buckets are there, right. And now I will have to see based on my angles value which bucket do I fall into, okay, out of these three. So suppose I fall into, so I said what angle did I say, 89 degree. So I will fall into this bucket, right. So now based on what bucket I fall into, I will look at some of the neighboring pixels that I have, right. So you have this Q and R. So you have to go back to the slides and see which pixels I am picking based on my angle. But suppose if my orientation angle is 89 degree, then I go to this block and I pick up one Q, which is a neighboring pixel of mine, and one R, which is another neighboring pixel of mine, right. So in this way, based on what angle I am at, I will see which bucket I belong to, and I will find out the corresponding neighboring pixels of that, right. So there is a logic behind it which you can go back and look at. And now what I am trying to see is, if I am greater than my neighboring pixels, the Q and the R that I picked, if I am still greater than that pixel, then I am going to retain this particular ijth pixel as my edge point. So whatever is in here, I will store that if I am higher than both Q and R. Otherwise I will put it as 0. 0 means what? That I have not detected any edge here, and non-zero means if I have this Zij equal to image ij, that means at ijth location I have a gradient that is there, okay. So that is all that is there to non-maximum suppression. So I am looking at my neighborhood and I am trying to see if I am special, if I am better than the neighboring pixels. How to pick up that neighborhood is given by this block of code, where I select the angles, select based on the angles. So what angle, what is my orientation angle, based on that which bucket do I fall into, based on that I will select this Q and R. That's it. So now I will run this non-max suppression algorithm on the gradient matrix and the theta matrix, right. So the gradient matrix is what we found here through the Sobel filter, and the theta matrix both. So on the gradient matrix I will do this operation, right. So now what has happened, so the resultant output of this operation is that you are retaining some of the gradient value magnitudes, you are eliminating some of the gradient magnitudes. So that is what you are doing. Yeah, so that is what you are doing. So understand this, that in this way I am so suppose here, like if we look at this particular, these two images, so because I have run the Gaussian kernel, because I have convolved my image with the Gaussian kernel, my image has become a lot more blurrier. So now the edges that I will try to detect, they will not be as sharp as this one, right. So there will be like multiple lines of lines of pixels that will be detected as the edges here, but I need to actually only detect maybe 1 or 2 lines out of them. So this I will do using the non-maximum suppression. So I will select images, I will select pixels out of a neighborhood where the pixel is the strongest one to carry the edge information. That's it. Now linking and thresholding, like I said, is very simple. So the idea is simply this, that I will have a high threshold and I have a low threshold. So in Sobel we had only one threshold. So if my gradient magnitude was higher than that threshold, I would select that particular pixel value to be that particular location to be an edge point, otherwise not. Here we have 2 instead to make things a little bit better. So what is the algorithm once again? So if I have a suppose if my edge point, suppose if my edge point is greater than this high threshold, so if my gradient magnitude is greater than this high threshold, I will simply say that the corresponding pixel location is an edge point. If it is lower than the low threshold, that is lower than the 0.05, I will say that okay, the corresponding pixel location is not an edge point at all, eliminated, that is it. However, if it is in between the 0.05 and 0.09 or whatever the high and low thresholds are, then we will have to run an algorithm. The algorithm is very simple. The algorithm just says that suppose if there is an edge point in my neighborhood, then I am an edge point, otherwise I am not, that is it. So so here you can see very clearly that if it's if the image at a location is higher than the high threshold, I will retain the values. If it is lower, then I will basically not retain the values, and the weaker ones are where the weaker ones are where we are in between the high and low values, right. So now and I will retain them. So once I have detected what are the points that are lying in between these two, the next step is called hysteresis. So hysteresis does what? Hysteresis says that okay, I will retain, like I said, I will retain a edge point which is a weak one, by the way. So I will retain a weak edge point if on its neighborhood there is another strong edge point. Okay, so that is what is implemented here. So there is a lot of for loops and all, so you can go through the code. So this will give you an exact feeling of what is going on inside Canny. So that is why I wanted to show you this code. So this linking and thresholding is what is making Canny edge detector so different, because you can see that in the first step the Sobel operator is still there. So the Sobel where is it? This is a subset. So the Sobel which we described as a edge detector is a subset of the Canny edge detector. So the last 2-3 points, they are the most important ones which makes it different from all the other edge detectors. So finally when you run Canny edge detector, the hysteresis function is the last one, which basically selects which weak points are true edge points and which are not. So once you run this, you get the final image. final edge point. So you can see that, let me zoom it a little bit. So all these, the brown lights that were there around this circular thing, all of them have come. You can see even the twinkle that has come in this star, right. So the original image was wait, where did it go? Yeah, the original image, you can see there is a twinkle here. So Sobel was not able to detect that. Sobel had just detected a spot here. So this image has been able to even detect the twinkle that is there. So Canny is a very powerful edge detector. So yeah, I mean, you should go through the code, and for more details you should refer the slides once again and the code together. So this is about the Canny edge detector. So now I wanted to maybe not give you a very detailed walkthrough, but a little bit of SIFT also. So let's switch. So we'll share these slides with you, these codes with you as well. So let's, okay, just give me a second. Yeah, maybe there's a connectivity issue, that's why. Yeah, got it. Yeah, let me share my screen once again. Yeah, okay, now that it has come up. So yes, so this is the SIFT algorithm. So this also we'll share. So this is more for your own benefit, to understand what is going on inside SIFT, because it's not a very easy algorithm. So it's not like I would say that once you go through the deep learning algorithms, you'll find probably you'll find them to be a little bit easier than these. But to understand SIFT and the other state of the art algorithms that were very good at that point, you should go through the code of them, right. So here, like, I just wanted to give you a overview of what are the function blocks that are present, so that you can go through them and you can play around with them as you like. So like we had talked about, so there are 4 steps in the SIFT algorithm as well. So one is detecting interesting key points, one is localizing them, one is estimating their orientation, and finally attach a descriptor to each key point, right. So these are the 4 steps that we had. So yeah, so these are all the basic building blocks that we have of to basically compute the SIFT vectors. So is anyone, yeah, so we'll give you, Hatim will give you these codes that are there as and when we walk through them. Okay, yeah, these will be uploaded, Praveen, don't worry about it. All of these codes that we are showing in the class, we'll upload them. So nothing to worry about that. So I'll upload it right after this class maybe. Yeah, so there are multiple parts to it. So here you can see the number of octaves is one function, Gaussian kernels. So generating Gaussian kernels is another function. So Gaussian kernels we have to generate, right, because we want to calculate the scale space, which is basically an image convolved with Gaussians and all. So generate Gaussian images, DOG images. So DOG is the space where we are calculating basically we are calculating the key points. So finally this find scale space extrema is the final algorithm that you run to get the first interest points, right. So this duplicate key points, this part basically eliminates some of the bad key points. Then these two are basically, finally we require these two to generate the descriptions. So you can see that yeah, so generate base image, this the next function that is there. So this this function generates the base image from the input image by upsampling by 2 in both directions and blurring. Basically this function doubles the input image in size and applies Gaussian blur. So this is one simple function which will basically take your image and increase its dimension, and so basically so increase its dimension and blur it with a Gaussian kernel. So as simple as that. So you can see the similar blocks of code where we are reading the images. So you can put your own image here and you can see whether the SIFT algorithm what it's generating, and similarly for the other code block also where you are detecting edges, you can just give your own image and see whether it's detecting the canny edge detector, how it's doing, that you can see. So this is the base image that we generated. So so this is the base image that we generate with the generate base image function, and then this is what the base image looks like. So this is what the base image looks like, it's that of a dog, right? And now this particular function is for generating the number of octaves, so compute number of octaves. So you can go through all of this. So compute number of octaves in image pyramid as function of base image shape. So this function computes the number of times we can repeatedly half the image until it becomes too small. So like we showed in this particular slides, so it's basically saying that we start with the bigger image, then we go smaller until it's too small to visualize. So it's just giving you the number of octaves that we can have before making the image too small and unreadable. So now this is what we calculate in this numoct variable, and we get the value to be 8. So basically we can have 8 octaves of this particular dog image. And now we have to generate Gaussian kernels. So here you can see that the base sigma is given and the number of intervals is given. So based on that you can go on generating the Gaussian kernels. So you can see that Gaussian Gaussian kernels is a variable. So it's basically nothing but an array of this number num images per octave, number of images per octave. So so this is given by the scale of Gaussian blur necessary to go from one blur scale to the next within an octave, right? So this first one is given by the sigma itself, and then whatever based on the formula that has been taught in class, the next Gaussian kernels are generated. So these things again you can go back and have a look at. So these are the kernels that you get. So these are basically the sigma functions. So from 1.6 to 3, these are the sigma values that you get. Okay. So now this part is basically generating the scale space pyramid of the Gaussian images. So this part generates the scale space pyramid of the Gaussian images. So this is similar to if we go back, so scale space is given by this, right? So we have the Gaussians with us, we will generate the scale space for each of these scales basically in a given octave. So that is given by this function, right? And so these are all the images that you, so for a given octave, these are basically, if you finally visualize, these are the images that are getting generated. So this is the original one. You can see that the second one is a little bit blurrier version of the original one. This is a little bit more blurrier, and up to this, which is much blurrier than these, all of these. So finally you generate the DOG images by computing the difference of Gaussians. So here you can see that just by looking in a cursory glance, you can see that you are subtracting the second image from the first image, like we do to generate the DOGs, and we finally so this function generates the difference of Gaussians, and it gives you the pyramid. And now finally you have the key point function, localize extreme localize extremum via quadratic fit. So yeah, I will not go into this. So this is pretty involved, but this is just to give you a feel of the fact that these are the steps that go inside the inside the SIFT algorithm, and this is for you to explore. Basically I am just showing you the different steps that are given in the particular notebook. So now you'll first of all you have to find out the neighborhood, like we told in this way. In this way you look at the 26 neighbors, and then you also basically you find the so this particular function is basically like a combination of the key point localization and also the final key point detection. So these things you can go look at your own time. So the math, the code is a little bit involved, but yeah, it does basically everything that you would want. And finally this is the, so this at this point, at this particular cell, so okay, did I, yeah, okay, cool. So once this particular cell is done, now we are going to compute the orientations. So based on how sir had taught, we look at the different orientations of the key points, we divide them into beans, and then we compute a histogram of bins, and then we select the one with the highest value. So I am not going to go into that, but this is how we estimate the orientation of the key points. And finally once all of these points are done, so we will get just a second, so finally firstly we will get this sort of an image which gives us the interest points. So like I said, the length of the arrow determines the magnitude of the key points, and the arrow direction determines the orientation. And finally this is what you get after after filtering some of the bad key points, some of the unnecessary key points. This is what you are left with. And finally you generate the key point descriptor. So yeah, like I told you, so this is a pretty involved piece of code, so just go through it on your own time. So this is the descriptor that you get. And now suppose, just to show you an example, so this is the input image that you have. So this is input image 1 basically, and now what you do is you also so let's go back at the input image. So you can see that this is an image of books, right? So this is the first image that we have. And suppose now, so we already know what are the we know how to run SIFT on it, and we know how to get the key points and the key point descriptors. And now what we want, this is the image this is suppose another image that is given to us. So you can see that it's denoted by image underscore 2. So this is another image that is given to us, and it consists of I hope you realize that this consists of a snapshot of the previous image. So this is like just 3 books out of the stack of books that we saw there. So yeah, so there are many books here, and that other second image is like a subset of this. So it's a snapshot of this part, the one that I showed. And now you are trying to basically match these two, and finally you are able to see that so in the final output image, so when you are trying to match the key points, you will see that this is the second image and this entire thing is the first image. You will see that it's able to identify what are the matching key points. So basically the descriptor that it wrote is basically robust to these changes. So it's able to detect these to be similar as this particular images, these particular books. So I know I kind of went very fast here, but yeah, the objective was not to give you a full walkthrough here. So these are some of the exercises that you need to do on your own to understand what is going on here. So you better do that if you want to learn more about SIFT. So yeah, so I'll share this document with you, I'll share this code base with you. Make a copy of this and then play around with it, try to understand the huge amount of code that is there here, so you can understand how difficult and how involved this algorithm is. So it's not very easy to explain all this code. I mean, there are so many lines of code that is involved in running this single algorithm. So but the speciality of such algorithms is, even though they were complex in nature, you can see that this entire, so if we look at all these 4 steps that are there, none of them depend on any previous data, right. So you do not have to get millions of images, and you do not have to train this algorithm on those millions of images to generate some good semantic vectors, but you just need to run this algorithm and you will get pretty good vectors out of any image. That is the advantage of the pre-deep era. So the math that goes behind it, it works for everything. So while maybe not, I mean, in today's world with better deep learning models, these algorithms are becoming a little bit obsolete, but still in some industries they are really, I mean, simple situations, they are pretty useful. So yeah, I would request you to go through this on your time and you'll get much more insights on the algorithm. So this is more or less what I had in oh okay. So Praveen, I mean, was my screen not visible till now? I think I shared it actually. I was sharing the entire screen only. Okay, no problem. Okay, so if you are not able to see it, no problem. So basically what I wanted to communicate was that we have I'm going to share a notebook with you, which consists of the entire SIFT algorithm with the descriptions and comments on all the 4 steps that are there in all the 4 steps that are there in SIFT. So my request would be for you to, I did not explain too much of it, right. So I just maybe gave you an introduction of what each of the function names may mean. So you have to go yourself and have to look at it and understand, and basically whatever algorithm sir has taught you in class, you have to map that algorithm with the code that is there in the notebook, and you have to make the best use of it. So you can run it, you can try, I mean, you can use it for better understanding. So yeah, all of that is on you. So asking about the code, which code? Can anybody unmute and say I am not getting? Oh, okay.
You said you'll be sharing the code, right? Will Dharna share the chat or mail if you want to?
Correct. Sorry, my bad. So the code that code and the material that I have for today, so they'll be shared with you. So wherever, I mean, in your course link, I think you will find wherever we are uploading the regular video links, there only you will find link to a folder where we are dumping all the sessions and the particular codes and slides that we are using. So you will find it there. If you don't find it in the website, in the course website, just let me know next week, so that I can communicate to the concerned people. So you can also post on the discussion forum if you are not being able to access them. So we have already, so our part is to have a shared folder, Google Drive folder, and we are dumping all the material into it. So if you are not able to access that folder, you should post on the discussion forum. So I'll right away after this, so this week is over with this class, so apologies for not being able to take it on in the correct time this week. So with the completion of this week, I'll right now upload the slides and the code, the 2 code books that I showed, into the folder, and if you are not being able to see it maybe by tonight or by tomorrow morning, just write in the discussion forum in the course web page, and your concerns will be addressed. That's it. So yeah, this is pretty much what I had in mind. So yeah, I mean, we went through a lot of material in the last week also and this week also. So all of these are like image processing tools. So these are just to make you familiar with the history of image processing before the deep era came. So all of you should have some idea on these things. So slowly we'll go into the deep learning part of the course. So yeah, I mean, these are also very good and very simple tools to have. So that's why, I mean, we are taking these first 2-3 sessions. So yeah, you should go through it and make the most use of it. Yeah. So all these codes and slides, as I said, we have a folder for it where we are dumping them. and you should be able to access them. If you are not being able to access them by tomorrow morning, just post on the discussion forum and it will be taken care of. Okay. So yeah, fine everyone. So let's meet next week. Next class is on Monday, I believe, from one of our TAs. So yeah, let's meet then with a fresh week. Thanks.